Okay guys, as promised, I'm going to make a video and I'm just going to go straight through the Chapter 2 test review. So let's do this. I'll be using loose leaf paper sometimes. I might be going back and forth. Here we go. 1, evaluate the limit. So remember, we have a rule that says the limit as x approaches 0 of sine of something over that same something is going to equal 1, right? So I have sine of 2x, so I need that 2x in the denominator. For now, I'm just going to fill this in with x. Okay, so I'm going to rewrite this as the limit as x approaches 0 of sine of 2x, whoops, let's get a good start here, over 2x times 10, okay? Because we know that this thing here is going to have a limit of 1. So the limit of this is going to be 1, and this is going to be 1 over 10 left over. So my limit here is 1/10. Let's try this one over here. I can factor an x out of the denominator. So I know that the limit of this is going to be 1. And then I really have left over a 1 over 3 minus x. So the limit of this portion was 1. If I plug in 0, I get 1 over 3 minus 0, so 1/3. So my limit for this one is going to be 1/3. Okay, and remember we have those we really have those 2 new limit rules that we saw. So the limit as x approaches 0 of sine of x over x is 1. And then we also had the limit as x approaches 0, I think it was like 1 minus cosine x over x. So make sure you know those, okay? Let's move on to this one. I'm going to need more paper for number 3. So let's do number 3. We have the limit as x approaches 0 of this over this. Now we know we have to rationalize. That's our method. So we're going to multiply by the conjugate, which is the first part plus the second part, because this was minus, so we're flipping that. Whatever I multiply by in the numerator, I have to multiply by in the denominator. Okay. So I'm going to have the limit as x approaches 0 of, so we're really foiling. So it's this times this, this times this, this times this, this times this, right? But this term with these two and this term with these two are the same, except one's going to be positive and one's going to be negative. So this times this is going to give me a positive x plus 16. These terms are going to cancel out, and then I have a minus, so 4 times positive 4, so I'm going to have a minus 16. The numerator is the reason we rationalize, so I'm going to FOIL through here, but I'm not going to distribute in the denominator, and that's really important, and you'll see why in a second. Okay. 16 minus 16, that's 0. So now I'm left with this. Because I didn't factor or distribute that x, now I have an x in the numerator and an x in the denominator. Now remember, I really still have a 1 left over in the numerator. So now I can finally plug in the 0. Don't forget this 1. That's where a lot of people are making mistakes. Oops, I'm ready to substitute in, so I don't need this, right? So I'm going to substitute in. I'm going to have a 1 over, so square root of 16 plus 4, which is the same as 1 over 4 plus 4, which is the same as 1/8. Okay, so that's number 3. Okay, let's look at number 4. I'm going to use a sticky note for this real fast, and I'll show you why. Now, I don't know exactly what this looks like, but this is what I do know. At x equals 0, I have a y value of 3. I also know that everywhere before 0, I have some line, okay? And I don't know exactly what it looks like, but it might look something like this. Okay? After 0, I have another line. It might look something like this, okay? I don't know exactly what these pieces look like yet, and I could graph them correctly, but if I'm going to find the limit, I don't really care anything about what's actually happening, like the actual value of the function at this point, so this isn't really helpful to me. I really want to know if what I'm approaching from this side is the same as what I'm approaching on this side. From this side. So as we approach 0 from the negative side, well, this is when x is less than 0, so I want the limit of this. I'm just going to plug in 0 and I get 2. Now I want the limit from the right side. This is from the right side. I plug in 0 and I get 3. So what I'm approaching from both sides is different, so the limit doesn't exist. Okay? And I'm going to just write these answers in as I go. Okay, let's look at this one. If I plug in 4, if I substitute in, I get a 0 in the denominator, so I'm going to try factoring. I'm going to get an x minus 4 times x plus 5. I'm ready to substitute in, so I don't have to write the limit notation anymore, so I'm going to plug in 4, and I get a value of 9. Okay, this is a limit as x approaches infinity. Remember, a limit's at infinity, and we mean when x is going to infinity or negative infinity, is the same as our horizontal asymptote rules. So when my numerator has a larger degree, it does not exist. When my denominator has a larger degree, it's 0. When they have the same degree, it's you take the ratio of the leading coefficients. Well, in this case, the numerator has a larger degree, which means that my limit does not exist. Okay, number 7, I'm definitely going to want more space for. So let me just start by writing down. Okay, so the first thing that I want to do is I need to get a common denominator for the numerator. So I'm going to need 3x. So I'm going to need, for my common denominator, so I'm going to multiply this by 3 over 3. And I'm going to get 3 over 3x. And I'm going to multiply this by x over x. So I'm going to have x over 3x. And then I still have an x minus 3 in the denominator. The next thing I'm going to do is I'm going to actually combine the fractions in the top. So I'm going to have a 3 minus x over 3x all over x minus 3. I have a fraction divided by something, so I'm going to take the fraction and I'm going to multiply by the reciprocal of this. Okay. Now this next step you might not choose to show, but I think it's important to make sure you understand what's happening. This is the same thing as negative x minus 3. I'm just pulling out a negative. And the reason I'm doing that is now that factor looks exactly like the factor that I have in the denominator here. So I get rid of those. Don't forget that negative. So now I have the limit as x approaches 3 of negative 1 over 3x. Now I can plug in my 3 or substitute in it. Okay, so that's number 7. Remember, you can pause this video at any time, so if I'm going too fast, you need to write something down, or you need to listen to something again, you can always go back, okay? Let's look at number 8. Use the definition of the derivative, so the limit definition of the derivative, to find the equation of the tangent line through the given point. Leave your answer in point-slope form and show all work. So let's do that. So for number 8, my function is this. And I want the equation of the tangent line at 4, 45. Okay, I have two options for what I can do for the limit definition of the derivative. I can do the limit as h approaches 0 of f of x plus h minus f of x all over h. Or, because I want the limit at x equals 4, I can also do this. Now, normally instead of 4 it says a, but we know we want it at 4, so we can do it like this. I'm going to choose to do it this way because I find when I actually know what point I'm at and I don't need the overall rule for the derivative, this is my better option. Now, on this unit right now, I know a lot of you have learned how to use the power rule to take the derivative, but we're pretending at this point that you don't know how to do that. So the only way we can take the derivative is with the limit definition of the derivative. So I'm going to choose this one is what I'm going to use. So here I go. F of x is 3x squared minus 3. I want f of 4, so I could plug it in and I get 3 times 16 minus 3, but I already know what it is. They told us that value. So this is f of 4. So minus f of 4 over x minus 4. So that's going to be 3x squared minus 48. We're going to factor out that 3. So we have a difference of squares. And now finally I have that common factor in the numerator and the denominator. Now this is totally a different problem, but remember when I have a common factor in the numerator and the denominator, that's going to turn in graphically into a whole. So don't forget about that. This is not going to be a vertical asymptote. This is going to be a whole. But when I'm solving the limit, I don't care about wholes because limit's what we're approaching. It doesn't matter if there's a hole there. Okay, I can finally plug in 4. Set 3 times 4 plus 4, which is 8, times 3, which is 24. So that's my slope. So remember, when I'm going to do the slope, I'm going to do the equation of a tangent line, I'm going to use my point slope form. So y minus y1 equals the slope times x minus my x coordinate of my point. Well, my y coordinate of my point is 45. My slope is 24. My x coordinate is 4. And you're going to leave it just like that. So that's number 8. We have to use one of the limit definitions of the derivative. Remember, this gives me a generic rule for the derivative for the function. This gives me the derivative at a specific point. And then I have to use my point slope form to find the equation of the tangent line. Okay, I'm going to move on to number 9 now. Number 9 says, use the intermediate value theorem to determine if there is a 0 in the given interval. Clearly show all work and state your answer as yes or no. And then remember, if I said justify your response, you're going to have to give me a sentence. So we're going to practice doing that too. So I want to know what's happening on this interval. So these are my x, my endpoints. So first thing I'm going to do is say, what's f of 0? If I plug in 0, I'm going to get 0 minus 0 plus 5. And if I plug in 1, I'm going to get 3, so negative 6 plus 5, so negative 1. Okay? If I were to graph this, and I'll do this real fast. Okay? I'd have a point at 0, 5, and a point at 1, negative 1. Right? We want to know if there's a 0. Well, if this is continuous, I know this function's continuous because it's a polynomial. I have to cross through the x-axis to get from this point to this point. So yes, there will be a 0. So we're going to say yes, there is a 0 because, so I should really say, sorry, yes, there is a 0 on this interval because my function, so f of x, is continuous and f of 1 is less than 0, which is less than f of 0. I think I didn't phrase this well. So yes, there's a 0 on this because my function is continuous. So I kind of have to add in, therefore I can use the IVT. Hold up. Sorry guys, I'm going to write this one more time. I'm going to rewrite this. Let's just do it like this. Yes. Because f of x is continuous. Sorry guys, the reason I'm rewriting it is because I wasn't able to get my point about the IVT with it grammatically sounding good, if that makes sense at all. So let's make sure we got all these things in here. So yes, because f of x is continuous, I have to have that. And my endpoint values straddle 0. So because f of x is continuous and this, by the IVT, there must be a 0 on this interval. Okay, so I hope that helped. So you have to mention that it's continuous. You clean your endpoints, and I want to see the numbers to prove it. So then I can say by the IVT, there must be a 0, and I have to say on what interval the 0 is on. Okay? One of the things in calculus you have to do is write very specific, clear statements. Like you need to tell me which function, where on the function, like is the right value in between like the endpoints, which is very, very clear. Okay? Okay, number 10. Sketch a graph of f of x given all of these things. So let's do it. Okay, we know that there's a point at -2, 2. We know there's a point at 0, 1. We know that the slope of the function at 0, that's what that prime is telling us, it's the derivative, so the slope at 0 is 0. We also know the slope at 1 is 1. So I don't know where the point is exactly, but if I'm estimating that it's going to come through like this, it's probably going to start going up like this. So I would say by like around here, I can have the right slope. So slope of 1. And at 4, it's going to have a slope of -2. So let's say this comes in, and then it's going to have to go back down. So maybe around here, it could reasonably start going back down that steeply. Okay. Really, I just want, if it's a slope of something bigger than 1, just make sure it's steeper than that, right? So let's have it come in. It's going to go flat, right? Then it needs to go through at 1 like this. And then it'll need to come through kind of like that. Okay. So remember, these 2 points, we knew exactly where they needed to be. And for these 3 points, I had specific slopes that it had to be. So here's an example of what that might have looked like. Number 11. Find the average rate of change of y with respect to x on the interval this, where, and so for this one, y equals this. Here's my interval. So this is going to be f of 1 minus f of -1.